Thank you for being here. Thanks for having us today. We have prepared a little talk to you about real-time demand reporting based on MongoDB. Our goal with this session is we would like to give you 3 takeaways out of this. One thing, obviously, we want to provide at the end of our talk simple to copy solution for real-time demand reporting. Secondly, we will guide you today a little bit through our history we had with MongoDB. We will explain you a little bit the experience we had, the pitfalls we discovered, the good things we discovered, and that might be helpful for one or the other of you who is also considering to use MongoDB in his or her company. And thirdly, and maybe this is the most important part today, we want to describe how much sense all this cross-functional approach makes, how much sense DevOps makes, and how indispensable basically trust and freedom and responsibility in an environment in our world is for technical-driven innovation. So let us start with introducing ourselves a little bit. So we are from mobile.de. This is our office is in Berlin. We are a vehicle trade site. We are market leader in Germany. We have also a Polish site. We have currently like 7 million unique visitors per month, 2,000 PIs per second, so that's the environment we are talking about. Ingo?
Yeah. I'll shortly introduce myself. So I'm Ingo. I'm a sysadmin, have a Unix background. Been working at Mobility in the SiteOps team for about 4 years now, and I'm a firm believer in DevOps.
Yeah, cool. So my name is André. I'm a classical software engineer, so I work with Java, and besides great technology, I'm very interested in agile development processes. Okay, so let's move pretty quickly to the actual topic. All the story basically started like around 2 years ago, so at this time it was Ingo and I, we were kind of looking for some interesting things to do, if I can put it this way. It was nothing else than just feeling the need to try something out of the normal, out of the common. And we all believe, I'm sure, in the fact that all our effort should be very customer focused and that all our effort should turn into customer value. That's extremely true, but it's also true that every now and then you want to kind of play around with new technology and try something just for yourself. And it was also a pretty open thing. We wanted to do something no matter what. And at this time, NoSQL has been one of the hot topics. And of course, we understood pretty quickly that all the theory behind that, all the ideas with document-oriented storages and so makes a lot of sense and could also bring us technology-wise pretty much forward in our company. The thing was just, how can we make it happen? How can we basically try something out without risking our business? And so NoSQL was. We were discussing about what kind of technology can we try, and the first thing was we were basically checking the communities, reading about other approaches, and to cut it short, MongoDB seemed to be the most promised approach. It is a document-oriented storage, JSON-style documents, which makes a lot of sense in our environment because basically what we always do is like presenting data which is stored somewhere on the front end. And it built in replication and sharding, which is a very important thing when it comes to questions about scaling and so. The map and reduce framework was quite promising. So to cut it short, we just read a lot of documents, read a lot of talks, and then decided, let's try out whatever with MongoDB. If you don't really know, if you are not familiar with document-oriented databases, this is a little translation map, so to speak. So in relational databases, we speak about tables. The same thing are more or less collections in document-oriented databases. The difference is pretty clear. A table has a very strict schema, while a collection is just a container. You can put anything into it. But the mapping would be collection is equal table. A document would be what a row is, and a field would be what a column is. So in this case, you can basically build a relational database schema in a document-oriented storage. Not that it would make a lot of sense, but you could do that. By the way, if you have any questions or so, if you are too fast or whatever, just ask right away. Just interrupt me. Okay, Ingo.
Yeah. So of course, one of the very interesting parts of MongoDB was the promise of auto scaling and the high availability as well. And so let's shortly introduce the two technologies used here. So the first one is the ReplicaSet. So this is basically MongoDB's answer to high availability and scaling reads. And just a short question here: who is familiar with MySQL replication? Okay, a few. So you can think of the replication part is very similar to what MySQL does. So basically, each write is logged in a op log. This is an analog to the bin log that MySQL has, and this then is replicated to all secondaries and applied to the local state. And the main difference here is that on top of this replication, MongoDB has a bunch of nice features that automate failover and all of this. So in essence, a replica set is a cluster of nodes. Any one of those nodes can be the primary, and the primary is determined by a consensus election. And as mentioned, we have auto failover. So if our primary fails, if enough nodes are remaining online that a quorum can be reached, then a new primary is voted and or elected. Also, we have auto recovery. So if one of our nodes fails, and basically our data here on this node is corrupt, we don't have to copy a tarball, unpack, and hope that everything runs. MongoDB has integrated resyncing feature. So if he notices, hey, this doesn't work, you just delete the data here, and he will synchronize on its own everything. This is pretty nice. And how do clients connect? You have drivers, of course, for most languages, for Java, Python, Ruby, even Erlang, stuff like that. And usually what you do is, for when you're connecting, you provide a list of all your nodes, and the driver then will automatically determine which one is the primary, and that way know where to send write requests. Of course, so we have a single primary, so we don't have active replication. So all writes go to the primary, and reads by default go to the primary too, but you can set a flag per connection. When you set this to true, this is the slave OK flag, then reads will go to your secondaries. And that way you can scale up your reads. Any questions so far? Looks good. Then we come to the next nice auto-scaling feature is sharding. Who here is familiar with the term? Yeah. So this is basically horizontal data partitioning. In a lot of databases, you have to do this on your own. MongoDB has this built in. So what you have to know is that you shard your data on a collection basis. So it's not that everything will be distributed across shards. You enable this for certain collections where you think this is necessary. The important components here are we have another service, the MongoS. And this is a separate daemon you run, and you can think of this as as a routing service. This is also the service where your clients will connect to when you're working with sharding. So your clients no longer connect directly to the replica sets or to your shards, but they connect to this routing service. The next component are config servers. These are special MongoDB instances where all metadata about the sharding is saved to. And last but not least, of course, we have our shards. So usually a shard is a replica set because, of course, we want the high availability and read scaling. But for test purposes, we could shard over single MongoDB instances. Any questions to this? Okay. Of course, now let's get to a little bit more detail about how the sharding works. When we shard a collection, we have to determine a shard key, and this shard key determines how our data is distributed across shards. So a shard key must be a field that exists in every document, and you also need an index on this field. Yeah, and of course then your data is partitioned into chunks. These are basically value ranges of your shard key, and these chunks then are distributed across your shards. Here on the left corner you can see an example output. Here you can see that my shard key is the UID field, and then you can see that each chunk is delimited by 2 numbers, and all data that falls into this range is part of that chunk. And you can see that our shards are distributed. A few are on shard 1, and then you have a few on shard 2. And so the question is, how are the chunks distributed? So this is what the balancer is for. The balancer is a subprocess running on the MongoS instances. So in this case here, the balancer, we're not talking about traffic balancing. We're talking about balancing our data across our shards. And so we've been talking a lot about chunks. So yeah, a chunk has a maximum size. By default, this is 64 megabytes. And chunks are split automatically when a chunk grows bigger than this maximum size. So for example, what happens when I have a collection bigger than 64 MB is that if I enable sharding for this collection, I have my initial chunk, and if this is bigger than 64 megabyte, it will be split. So if I have a lot bigger collection, then I will of course have more than 2 chunks, and then the balancer kicks in and distributes my data across shards. Everything clear so far?
So one question, can you change the number of shards in existing database?
Yeah, so the question was, can you change the number of shards in a live setup? And yes, you can. You can just add another shard, and then the balancer process will kick in and redistribute your data. Yeah. Okay, so we looked at all of this and we were like, okay, this sounds great, so we have a really nice solution, and yeah, we sort of went looking for a problem.
Yeah, so this was really a very important point when we speak about innovation, because we knew in theory a lot about MongoDB. We also had it up and running on our local machines, but that was obviously not enough. We needed to find a challenge which would really prove how good MongoDB is or how bad it actually is. And so yeah, as Ingo pointed out, we were basically there with a solution and needed a matching problem. The thing with this problem we were searching for is we couldn't just risk any business value, right? So we couldn't just grab a business project and saying, okay, my friend, the next time we just build this feature based on MongoDB, because we had no idea how reliable the MongoDB is. We had no idea how much we could actually trust all this implementation, and so we couldn't obviously risk whole business projects. So we needed a problem which was, which solution was not pretty important to the business. So we didn't want the need to succeed. That was the most important thing. And of course, we needed a problem which was challenging. I mean, just taking a simple problem doesn't help, because we need to prove that MongoDB is really, really good if you want to use it for real business features, functionality. And yeah, we have been pretty lucky in this situation, because we had actually one functionality which was permanently causing issues. This was our demand reporting. So demand reporting means, in our case, we have two important pages on our site. So one is a search result page. So a person would search for a certain type of car and would then get a list of all available cars. And the cars which are most interesting to you, you want to see on a view item page. You can basically open a new page which shows all the details of this car. And you need to know that our main customers are professional car sellers. So what they want to know, what they want to understand very quickly is how interesting is my advert for the consumers, for the buyers. So what we delivered them were like performance indicators. And one of those indicators was the number of clicks, the number of views, so to speak. We had a solution for that in place, and in a minute I'm going to tell you how this looked like. The thing with this solution was that it caused permanently prod incidents for very specific reasons. And the good thing on this problem was it was very obviously a very high traffic use case. I mean, this is our most popular page. And so we couldn't possibly find a more challenging use case when it comes about performance questions, right? So yes, we decided then, let's try to re-implement demand reporting based on MongoDB. Yeah, some important key facts. So we wanted to count the hits per advert, but also we had another dimension which was the publisher. So we have, for instance, a site in Poland and we have a German site, and our car dealers want to know how many clicks come from the Polish side, how many clicks come from the German side, and also how many clicks comes from the mobile application. They want to know that, and so we had another dimension that was not just the number of clicks, but also, yeah, it was a little bit more complicated then. Performance-wise, we speak about 1,200 hits per second we needed to count for 2 million adverts. That was a challenge. So far, how do we did it so far? The old approach was actually, I still find till today, pretty smart. So what we did was we would write entries into log files, would then once a day process all the log files, and then write the result into a MySQL database. Yeah, this was a daily cron job. It was pretty long running. Only storing the result into the MySQL database took like 8 hours, and it was pretty error prone. I mean, you can imagine if basically during those 8 hours something goes wrong, and you either lose data or you duplicate data. You can possibly basically just reprocess all this without creating wrong data. So this was going to happen permanently and was really an issue. In this situation, I would say, very good for us. So, you need to remember that our goal was not in this moment to build a better demand reporting. What we wanted to do is we wanted to drive MongoDB to its limit. We wanted really to stretch it. We wanted to explode. I wanted to see this MongoDB instances basically to shut down. We wanted to see the limits of this technology. And that's why our first approach was, so functional-wise, not pretty smart. It was pretty straightforward. So what we first simply tried out was like, we write every single hit we had on our page, on our main page, directly into a MongoDB cluster and see what happens and see how fast it explodes. Here just a little bit about the setup. We had more things to measure than just page views. There were also the number of contacts a person makes, also number of how often has this page been printed. But those use cases are pretty uninteresting because they're very low performance if you compare it with the page views. So we then decided that we have just one collection per event type. So we would have one collection which would contain all hits on our view item page. This document contained a timestamp in the publisher, and of course the advert ID. And yeah, one more important thing is, of course, this is a pretty edgy use case, so we couldn't possibly risk to break or just to slow down our main use case. So what we did then is we decoupled this logic pretty much from the main threads. We used the thread pool with very limited number of threads and basically tried to do the communication with MongoDB concurrently for making sure that our main use cases are not affected by our playing around. Actually, it was not more than just playing around with an unknown technology. Good. So setup, that's your part.
Yep. Okay, so our goal was, of course, to play with MongoDB and learn. So we decided against starting with a full-fledged sharded cluster. And yeah, we just took hardware we had lying around. So these were, I think, application servers that were running out of warranty. And so we started with a single MongoDB instance and started playing. Then we noticed, hey, we want to scale our reads. We need this data, highly available, right? So we migrated to a ReplicaSet. And after a while, yes, our smallish disks were running full. So we had the need of sharding. And what's quite nice is that all of these migrations we could do live. We didn't need any downtime for this. And in part, at least, you can almost do this backwards also if you need to. You need a little bit of time for it because the steps take a little longer, but I mean, it's pretty nice to being able to scale up without any downtime. And so let's come to our first learnings. So of course, we're talking about lots of data, so I/O was our primary problem. And so the first things we noticed was that we were seeing lag on our secondaries, but there was no load on them. And then we figured out, the reason is that our primary is under such high load that our replication stream cannot be sent fast enough to the secondaries. So this is a thing to watch out for. And then also the balancer that distributes the chunks across shards also causes quite a bit of I/O, depending on how much chunks you have to migrate. And this coupled with our first learning can lead to secondaries lagging when you're moving a lot of data. But the solution for this is that the balancer can be scheduled. So what we did is we scheduled it for our low traffic hours where we had the spare I/O, and then that works out good. So when we're talking about sharding, so we said we have to specify a shard key. And we learned that you have to think a little bit about this, right? As always, because the first problem you usually run into is that you have a hot shard. So in our case, for example, the first field that came to mind to use as a shard key is our ad ID. So each advert on our site gets an ID. This is auto-incremented, of course. And the problem what you have then is, at least in our use case, is that newer ads get more traffic than old ads. And you always have one chunk that is from some number to max key. And so this chunk will get a lot more traffic. In our case, so in our test, we had 2 shards. And the shard with this max key chunk was getting, I think, almost 100% more traffic than the other shard. So this is a thing to look out for. And so you should really pick a key that has nice randomness, and also be careful because you cannot change this key afterwards, or if you want to change it, you have to re-import all your data. So, yeah.
It's possible to quickly change the key ranges for shots. Okay.
You can manually split, yes. Yeah. So yeah, you can manually split, but the problem you run into here is that, as in our case, we had the balancer running only in off-peak hours. So even splitting our chunk that was getting a lot of the traffic would not have helped us during the high time traffic, because starting to balance would get us more I/O. So if you have the spare I/O on your disks, then yes, you can do that. And so what the MongoDB documentation proposes is, so you can create a special field explicitly for this. So for example, we could have created a field that is the modulo of the add ID or something like this to distribute it more evenly. And in newer versions now, so short disclaimer, most of the stuff we talk about here regarding MongoDB is MongoDB 2.0. So this is from 2 years ago. I'll try to point out everywhere where I know that they've made improvements, and this is one of them. So right now, you can shard over a hash of a certain field, which of course then gives you the randomness. The other possible solution, and that's the one we opted for, is to use a compound key. So your shard key can be a compound key over 2 or more fields. And in our case, what we then did is that we used also the customer ID, because as André said, most of our customers are professional dealers, and they don't fluctuate that much. And most of our ads belong to these customers. So using a customer ID and ad ID as a compound key worked out pretty nicely for us.
Can I have a question? Because you said
Yes.
that the number of shards can be easily changed.
Yes.
But on the other hand, you say that the method of spreading the keys is not cannot be changed easily. So if you change the number of shards, how can you prevent that this new shard cannot become a hot shard, for example? Picking the right shard key to avoid a hot shard has nothing to do with the number of shards you have. This is separate. This is a separate matter. Because if you choose your shard key in a way that your writes will be distributed evenly across the chunks you have, or if you have a read-heavy use case, it applies as well, right? Then it doesn't matter how many shards you have, because your operations will be distributed evenly.
I mean, the reason for this becoming a hot shard was the behavior of our customers, because they preferred the new adverts. But it's not technology related, it's totally business related in our case. That was the reason for one chunk becoming a hot chunk, so to speak.
What are the drawbacks of treating a shard? I mean, how does it, how, for example, query performance depends on the shard you choose?
I think the question is how does sharding affect the reading, the querying performance, right?
Yes. The way you shard, I mean, if you shard one way or the other, I imagine that the performance might
So how this works is that the MongoS is the one receiving the query from the client. The MongoS then has the table where he knows which chunk is where. So if your query includes the fields that are the shard key, then he will know exactly to which shard send your query. If he doesn't know this, so if your query is more general and he doesn't know which shard is the correct one, then he will query all shards and aggregate the answer or merge the answers. So if you do this, of course, this could be a little slower. So yes, you should also consider your queries when choosing a shard key. In our case, most of our queries are actually by our ad ID or by our customer ID, so this works out nicely for us. I hope that answers the question. Okay. So what we actually wanted to do, of course, was aggregating stuff, right?
And so MongoDB has a bunch of nice features for this. You have the group function you can apply to basically any queries. Problem here is that it has some serious limitations. They have been raised somewhat in MongoDB 2.2 and 2.4, but the main thing is that you cannot use this in a sharded environment because this only works if you're talking to a single shard. And so for us, in the long run, this would not work out. Also, we pretty quickly ran into the 10,000K unique groupings you could have. But yeah, the main problem was that it did not work in a sharded setup. So pretty soon, okay, so and also very quickly, what we're not talking about here now, but in MongoDB 2.4, I think they introduced the aggregation framework, which has a lot of nice features. But back then, this did not exist, so we had to resort to the map and reduce framework, which is actually pretty nice because you write your functions, your map and reduce functions in JavaScript. Almost everybody has JavaScript developers in their company nowadays, at least in web companies, which was actually pretty funny when you ask your front-end developer for help when debugging map and reduce jobs. But again, we have some limitations. The problem here is that the JavaScript code, at least in MongoDB 2.0, was executed in a single thread. This was mainly because caused by the JavaScript engine they were using, the one from Mozilla. With 2.4, they have switched to the one from Google V8, I think it's called, and so they are now at scales. But back then, yeah, single thread. So the only way to scale anything there was adding more shards, which, yeah, is not always that cheap in hardware cost. And also a problem was that as soon as you want to write your result into a new collection and not just have it in memory, your MapReduce job has to run on the primary, and we wanted to keep as much load from the primary as possible. Oh yeah, one nice feature I forgot is the incremental MapReduce jobs. So what you can do is you can merge your current result of a MapReduce job with the previous result. So you can add up stuff or whatever. Yeah, so one of the problems we ran into also with our MapReduce jobs was working set. And yeah, we won't forget this this soon. Working set is pretty important. So basically, it's the amount of memory a process needs at a certain point in time. And so in the case of MongoDB, this is basically the indexes you're using, and of course the data or the documents you're reading frequently. And so in our case, our problem was because we were logging raw events, right? And we had about 43 millions of those per day. So we were producing about 2 gigs of indexes each day. And you saw the hardware we started out with. We had at first 8 gigs of RAM and then 12 gigs of RAM. And so, yeah, you have 4 days or 6 days, and then yeah, your working set is bigger than your memory. And yeah, the problem we had done now with our MapReduce jobs is that yeah, we had a full table scan with each MapReduce job. We had some ideas on how to fix this. So of course, what we could have done, because we have the incremental MapReduce jobs, right? So we don't have to run the MapReduce job on our whole data set every time. So we could say, let's run it only for data from the last day. The problem is we did not have an index on our timestamp. So we only had the index on our customer ID and ad ID for the sharding. But of course, adding a new index increases your working set again, and you don't really improve. So we thought about splitting our data into smaller collections, and so the interval we started out with was, say, we have one collection per day, and that way we maintain we keep the working set a lot smaller. This should fit into our memory. The problem you have then is that you cannot leverage the auto-scaling features anymore, because you have to go faster.
There's a lot to come here.
So no more questions, please. No, so you can't use the auto-scaling features anymore, because remember, our balancer runs during off-time hours only. But I think somebody asked this already. So what we can do is we can manually split our ranges and distribute these chunks before. But this, of course, is manually work, and it's getting complex. But yeah, so what were our conclusions so far? We had learned a lot. We were able to work around every problem we had. You have to figure out how stuff works in MongoDB, and if you configure it properly, if you use it properly, you have no problems. So our confidence that we would be able to solve this problem with MongoDB was pretty high.
Yeah, so just to summarize all this from a developer perspective, MongoDB works painlessly. Of course, we have been pretty proud on that, what we learned so far, what we discovered so far, and I think when we speak about innovation or so, we have now reached a pretty important second point. We need to do something about it, what is also creating business value. So what we do is, Ingo already mentioned it, we basically went to our business guy, basically gave them some ideas, what possibilities we might have, and so on, and very, very quickly, they very happily grabbed the chance, and very, very quickly our Play Store basically moved into a serious business project. So they wanted to have a real cool demand reporting now that we told them we can have. They wanted it, and they wanted it now. That was very amazing. It's always the same thing.
And it's worth noting it, up until this point, this was our pet project. We did this on our off hours.
Just basically in the canteen, so to speak. So, okay, so we had some very specific business requirements basically suddenly being there. Okay, one important thing is we don't want to just to measure the hits in total, but also per day. I try to be very, very quickly now. You already explained that map and reduce has some drawbacks, so it's not really real time. You can make it much faster, but this comes with increased complexity. It's also something you don't want. So map and reduce is also somewhat dangerous, because if you have a map and reduce job which is running on the primary and doing full table scan, you can easily basically stop the whole MongoDB cluster for a certain amount of time. That's nothing you want. So let me speak about some pretty cool MongoDB features we learn about. So one thing, so MongoDB, in contrary to relational databases, doesn't really have transactions. Okay, you cannot just open a transaction, do whatever you want, and then commit a transaction and hoping that everything has been serialized and is in a consistent state. But what MongoDB provides is an atomic update. So an update on one document will be atomic. Okay, and another great feature of MongoDB is an increment operator. So you can basically say, like, increment the value of this field by X, by 1, for instance, if we speak about hits. Next cool thing is you don't need to say, so if we get a new advert and want to have the demands report in our MongoDB for that, we don't need to say, like, is there already a document for this advert? If not, then create it. MongoDB has an upsert command. You can basically write a query, then the update command, and if this document doesn't exist yet, it will create a document. Very neat feature, honestly. Okay. So if we should provide you one page with the solution for our real-time demand reporting, this would be it. What actually happens here, it's pretty simple to explain. The first JSON document you see is a query. So we say, like, find me the document with the ad ID so and the customer ID so. And the customer ID is there because customer ID is part of our sharding key. It's not necessary for identifying this document, but for performance reason, we need the sharding key there because, you know, Ingo explained to you before.
Yeah, but also, so if you're doing upserts, your query has to include the shard key.
Right.
Otherwise, it just fails.
Right. So the next JSON document, so starting from the inc to the last brackets, does the following. It increments the field overall.total by 1. It increments the field overall.publisher.site Germany by 1. It increments the field 2013-6.total by 1. And you see what comes out of it. We have basically a lot of increments within one command, which is atomic. And you see how easily that would scale. We have now our demand on daily basis, on a monthly basis, in total and per publisher. The real command looks much bigger because we have like a referrer as well, so we have more dimensions. But this is something which works out greatly. This is atomic, and you can add so many increments as you want. The document which results from this query looks like that. I try to be pretty quick with explaining. So add ID, custom ID is self-explaining. And then you see this subdocument overall, and this contains the subdocument publisher. And then you see basically the number of hits from per publisher. Is this clear? Yeah? So what we did now, don't forget we wanted to find out how cool MongoDB is. That was basically the beginning of all this story. What came out of it? I mean, the first thing I need to admit, we discovered honestly how wrong the numbers of our former solution were. So I said in the beginning that I found our first solution pretty smart. But truth is, for whatever reason, we have proven that those numbers have been terribly wrong. And with our solutions, they are very, very reliable. The better thing, which even resulted out of that, we have now, only a couple of months later, already several customer-facing features which are based on MongoDB. And we can do that because we have invested our time and we played around with this technology. And that really brought us forward beyond just demand reporting, right? And yeah, we have sufficient experience to operate MongoDB for very serious use cases. And I think this is the best thing which came out of our little play-arounds. Okay, follow-ups. What needs to do? What leaves us to do? We need to update from 2.0 to 2.4.
Yeah, I'm on that.
Yeah. We are going to build a REST API also, so currently it's so that our applications are communicating directly with the MongoDB. This is working very well, but from a decoupling point of view, you basically don't want to have every application dependency to MongoDB clients and so on. So we are building a pretty simple REST API based on Node.js. And there's a library for Node.js, so this REST API is basically ready, and the code is honestly like so. That's all the code you need to build your REST API with Node.js, because Node.js also operates with JSON documents. That's perfect match, Node.js and MongoDB. And yes, we are going to build more and more use cases with MongoDB, so we have total trust in this technology, and it also brought us a lot of nice things we couldn't possibly do without this technology. And I hope, yes, that's it. Thank you very much. Thanks for your attention.